with commercial aerospace or commercial or aerospace industry. So because, as you know, making any new aircraft program is a very, very capital-intensive exercise. So those very large, no recurring investments drive the desire for risk-sharing partners. That's why at the beginning of the aerospace industry history, you see Boeing pretty much building the aircraft ourselves. But now we are partnering with companies around the world to achieve that. And that's associated also with the fact that the modern aircraft are much more complex and require a lot more multiple disciplinary collaboration to make it happen. So also, there is aircraft manufacturing typically is or demand. It's a cyclic sort of demand, and which results in cyclic production challenge for aircraft company as well. So we need to have a way to deal with that and to share the risk. And of course, there's a regulatory agencies concerns about adopting new technologies because of the risk-adverse sort of mentality to a certain extent, but in one way it's also correct because we want to really ensure safety. And that also means that for aerospace applications, for any new technology to be adopted, brand new technology, 10 years to 15 years is the realistic time frame in order to test out really the feasibility and the reliability of the technology. So the modern commercial aircraft structures going forward will put a lot of emphasis on weight saving because with the weight saving, you will reduce the cost, but also reduce environmental impact by reducing fuel consumption, for instance, and therefore reduce CO2 emission. Well, currently our company has received a lot more order than we can produce in the next 10 years, probably. So there is really a need to accelerate the production speed. So the customer don't want to order one thing and wait for 5 or 10 years or even longer to get the aircraft. So, for instance, our 737 aircraft, which is one of the most popular aircraft that's in demand. In the past, we were making like 8 or 9 a month, but now it's 42 aircraft a month. So the production rate really has increased a lot due to the use of new material, but also streamlining the production process itself, which is a huge improvement over the years. So also the next generation of the product will need a much balanced material selection, which will include composite, titanium, aluminum, steel, and even lithium-based alloys and other materials. So going forward, it will be more and more going towards that as well. So there will be also a continuous pressure to reduce manufacturing cost. So as we know, 787 probably is the first commercial aircraft that has used a lot composite material, 50% by weight of the aircraft material that being used. So over the years, you can see that the application of the composite has been used, first of all, on military application to test it out, and then gradually increase to the commercial aircraft. So now both 787 and the Airbus 350 are using more than 50% of composite material. So it does change the game. It enables much more efficient or weight reduction, and therefore there's less fuel consumption. You can fly longer for the same tank of the fuel. So I talk about the composite application in Boeing 787, and traditionally aluminum was used much more than composite. But as you can see now, composite is about 50%, and some of the use of metal has been taken over by titanium still has always been there. So as you can see that with the modern development of the material and the structure, it does shift how the actual material type is being used in aircraft manufacturing. So innovation has been, apart from, of course, material and structures innovation, there are a lot more other innovation has been incorporated into the 787 Dreamliner, so which include both innovative system, technology, flight deck, and engine and nacelle, as well as wing design. So the overall of those innovation for the 787 has led to 20% reduction in fuel and carbon dioxide emission, for instance, and also below 2008 industrial limits for nitrogen oxide emission, and huge improvement in noise sort of emission, as well as reduction in maintenance cost. So as you can see from there, the innovation of the technology overall, as well as the material, has led to significant improvement of the aircraft performance. So if you see on this graph, over the years, there is a significant reduction both on fuel consumption as well as the noise level for the aircraft. In the early years, in the 50s, compared to now, the improvement is huge. So for instance, it's 70% improvement in fuel consumption and CO2 emission, and 90% reduction in noise as well, due to those continuous improvement and in innovation. So evaluation of the composite usage in commercial aerospace is due to a combination of all these. So as one is improved the material technology, so the actual through development of higher strength and stiffer fiber, as well as the resin itself, and also improved, because with the new material, it will come with the new manufacturing technology that will enable that from happening, and that's included automated process so that you can make the aircraft faster, as well as improved analysis and modeling. So it's not all by trial and error. You actually do some of the, develop some simulation that can help you to fast track both the development and the testing of the new material and structures. So there is also an increased focus on life cycle, looking at life cycle cost, but not just a material cost, but it's a components cost, as well as the whole life cycle cost of that component is being taken into consideration. So there are, of course, being a new material system, there are lots of challenges associated with composite application as well. So we need to look at traditional tools has been designed for design and monitor metals, but now it's composite. They have different materials characteristics. So you do need to develop that and train, the engineer need to be trained to be able to master those tools and analysis as well. So that's one part of the challenge. And of course, there's electromagnetic shielding issues because composite is not as conductive as metal. So you need to build in lightning strike resistance, and also you need to consider its connection with other metal parts. So there are a number of issues we need to look at: heat distortion, and also we need to look at how to link well with other materials such as titanium and fasteners and coatings, etc. So tooling is another important area, how to make those big structure, composite structure, and how to develop the tool so that you can make it every time reliably and etc. So the production technology will be part of the challenge for composite manufacturing because the size of the part is huge, like the fuselage. It's made of composite. So the size of that is huge, how to make that. And lastly, is not the least, is repair technology. When you have an accident, how you repair it. So fortunately, the 787, through the 787 program, we managed to develop and implement the practical solutions so far to all these challenges. So that's why today the 787 aircraft has been put into service and has been doing very well. So I talk about the 787 before. So the 787, through this program, we really productionized the large composite structure manufacturing itself through the tooling itself, fabrication, how to bond it with other fasteners or with other stiffeners or other metal reinforcement structures, and how to inspect it. And you can see the inspection is huge, how to make sure it's reliable and repeatable, and how to assemble it as a whole, as well as the repair. So that certainly, that program itself has allowed us to gather a lot of experience in composite applications. So looking forward for continuous improvement, we certainly look at we'll be very interested in multifunctional materials, which means that instead of putting multiple material to perform multiple functions, we would like to see one material, for instance, to perform multiple functions. In that way, you can achieve weight saving or weight reduction and cost reduction, etc. So we are also putting a lot of emphasis on multi-scale modeling and simulation of structural performance. So that means that instead of relying on each time just try and error, we want to build a big database whereby you can predict through simulation and models to better predict and more realistic predict the performance, so it can shorten the development as well as the testing and qualification cycle for building aircraft or developing a new aircraft model. So we are also interested in looking at novel architectures for performance improvement, like integrally stiffened structures, etc. So as you can see, that there's still a lot of room for us to innovate, and including everyone here can contribute to that. So other future technology enabler, including flexible automation. So in the past, for aircraft manufacturing, you have all fixed gigs for manufacturing, but now it's talking about flexible arrangements, so you can actually make the factory more flexible to manufacture and more adaptable. So that's one of the future trends. And also, we will be interested in looking at material that is environmentally responsive. Surface chemistry and coating certainly is one area we also want to look at to enhance the performance of the aircraft, both from anti-ice and from improvement of aerodynamics. And there are a lot of functional coatings that can contribute to the overall aircraft performance that we're looking at as well as inspection and effects of defects. Are there other faster and better method of inspecting the aircraft to ensure reliability, etc.? So despite of all the progress that we have made, there are still a number of ongoing challenges, such as speed, how fast we can come up with a concept, validate the concept, and certify the actual material or the parts. Currently, as I said before, it still takes about 10 to 15 years. So can we do it faster, and how to do it faster without compromising safety and reliability? So we also need to be mindful of the fact that we cannot just make a material and we cannot just develop a material, but cannot make it in a reliable and consistent and robust manner, and in a cost-effective manner as well. So that will be another area that we need to look at. We cannot just develop a material without considering its manufacturing ability at a larger scale. And also, the other more and more important factor is how to reduce the environment impact to build, operate, and dispose our material. So we'll continue to partner globally, and we put 3 costs there. So at the end of the day, innovation wants to be achieved and without, still at a cost affordable manner. So that's a very important part of it. So as a summary of that material and structure section is that we can see material and structure technology will continually to play key roles in the next generation of aerospace products. But however, there are lots of challenges for us to work together and overcome. So Boeing does engage globally in development of technologies, as you can see here